Presentation is by Dr. Mark Schwartz. It is entitled Airborne Biosecurity Comparison of Air Filtration and an Electrostatic Precipitator Technology. Mark is an assistant professor at the University of Minnesota, and he is working in the swine group as well as the Swine Disease Eradication Center. In this role, he contributes to research projects in PRRS virus, aerosol transmission, and surveillance and transport biosecurity. He also works at the intersection of disease control, elimination, and surveillance. He has served as a board member, one of the founding board members of SHIC, as well as the president over the last year of the Swine Health Information Center, and currently serves on the Minnesota Pork Board Animal Health Task Force. He's been involved in the U.S. SHIP initiative, serving on various committees within that organization, and continues part-time with Schwartz Farms, where he is the Director of Innovation and Product Optimization. So thank you so much, Mark, and looking forward to your presentation.
Thank you, Megan. And it's great to be here and on behalf of the entire team that carried out this project. I'm glad to be able to report the background and the results to date. And as Megan mentioned, it's a look at the comparison of air filtration and an electrostatic precipitator technology. This also is a result of funding from Swine Health Information Center, National Pork Board, and the USDA FAR as part of the Wean to Harvest Biosecurity Program, in which there is an RFP for alternative for bioexclusion. So the project is the development and evaluation of an electrostatic precipitator, or ESP, a prototype to mitigate airborne spread of pathogens under farm conditions. The objectives, firstly, develop an ESP prototype for field deployment in a swine unit, and then to assess the performance of the ESP under those field conditions. So again, won't spend much time on the background of this. I think we're all well aware of the data would suggest certainly that there's a role of pathogen transmission through aerosolized virus, the burden of disease, and filtration has been a tool in bioexclusion, right? Trying to keep virus out of populations, primarily boar studs and sow farms. The same group in this project and others were part of a publication in which we reviewed both proven and emerging technologies in this control of aerosolized virus transmission. And there's a number of them that are emerging and not validated, including ultraviolet C, ionization-based systems, microwaves, reactive oxygen species. Electrostatic precipitator is under the heading of proven technologies. And the goal when we're looking for alternatives is either increased effectiveness with equal cost, or increased effectiveness or equal effectiveness, lower cost, or some permutation around that combination, right? So electrostatic precipitator technology is not new. The first patent was filed, I believe, in 1907, utilized in power generation plants, coal plants, incinerators, et cetera, where they're trying to trap particulate that's being emitted from this process, using high voltage electrodes to capture these particles. This is how it works. I mean, you're moving your particles moving through this precipitator. The electrodes have a negative charge. In our prototype, I think it's 11 kilovolts, very low amperage. And so either the free electrons or ionized particles around the electrode charge the particles, give a negative charge, and then a positive charge collector plate, which collects those particles and keeps them from being emitted, or, in this case, from entering the airspace of the pigs. So this would be new technology for bioexclusion in swine. And so we're able to have access to a wean to finish barn, which happened to be filtered for reasons I won't go into. And we're able to access this with the cooperation of these growers and this top-down ventilation. And we're able to put the electrostatic precipitator in the air inlet room, get ductwork up to a filter box, remove the filters. And that was the electrostatic filter test chamber. The adjacent filter box then, in which we collected our data on the filter to have those adjacent to each other. Just a different schematic. So the air, again, coming in the end room, and the fans, and then there's also fans on the end. So we were working with these two, this filter box and this inlet with the ESP treated air. So another diagram, so at the ESP unit here, our upstream OPC, or optical particle counter, is placed here, our downstream right here in the duct. And for the filter box, the upstream OPC is on the truss, and then the downstream was in that filter box below the filters. So we're able to count particle ratios of incoming air and downstream air for both technologies. A closer look then of that ESP unit, and again, the upstream OPC, this is where the charge is occurring and the particle is captured. And there's our downstream OPC. This is the box here in which we had our laptop, our pressure transducers, all our USB ports for getting all this data back to Hassan back in his lab in the College of Engineering. I should mention this project is a collaboration of the College of Engineering and the College of Vet Med here at the U of M. So collection efficiency. What this is showing is on the x-axis, the particle diameter as measured by those OPCs, and the collection efficiencies. And it's a composite of many collection events in which we have 6 hours of collection times. Excuse me. And so in filtering, this is called the fractional efficiency on the y-axis. And it's showing the ESP on the left and the filter on the right. I also should mention this is a MERV 14 filter, and I'll go into some detail on that in just a bit. A function, collection efficiency is a function of temperature, and so in that, Hassan was able to look at those efficiencies by ambient temperature, etc. These values down here on the very low bottom, fractional efficiency on a MERV 14 would typically, down here in a 0.3 micron, would be somewhere down here. This is just very, very low particle counts in which it's hard to get a ratio of a numerator and denominator of any exactitude. This is a composite then, or a summary, I should say, excuse me, of all those previous collection events showing the fractional efficiency or collection efficiency by particle size for both the ESP in the red and the filter in the blue. So that's the collection efficiency portion of this, looking at that. Nothing really surprising, and we'll go through what that efficiency is on a MERV 14 and in just a bit. Through the pressure transducers, we're able to measure the difference in pressure drop inside each of those filter boxes. And as expected, we have a lower pressure drop with the ESP than the filter. Implications being lower energy use as your fans decrease in CFM moved as static pressure increases, and some work from several years ago from Dr. Tormorell and Yanni, again in engineering. As pressure drop increases, there's more bypass air going into the unit, into the building, and not through the filter or the unit it's intended to pull through. A number that's used in the bioaerosol engineering world that we don't use in filtering pig farms, but it's important, is figure of merit, and it's a metric of particle capture efficiency as a function of the fractional efficiency, which I mentioned, the pressure drop, and energy usage to get that capture. It's measured in volume per kilowatt, in this case meters per cubic meters per kilowatt. A higher number is better. And again, some assumptions, there's differences in fan efficiency. We'd have to assume that those measurements across barns, you'd have some stationarity in your fan efficiency. And there's more variation, as we saw in that previous graph, at the higher static pressures. So what it is, I'll spare you the details and the equation, but it's looking at the collection efficiency, the flow rate, the pressure drop, and the fan efficiency. And the one difference there is we have to add back in to the ESP the energy used to operate the ESP, right? So a fair amount of noise there, but at the higher pressure it would indicate a better figure of merit for the ESP over the filter, and the opposite in the lower, which makes sense as you're using energy to run the ESP unit and very low static pressure at that time to lower flow rates. The next question is ESP effective in reducing PERS from the air? So to do that, we used a virus aerosolization study, excuse me. So in that, we used PERS VR 2332, the prototype virus, grown on cells at 10 points to the 6.75 TCID50. Used the Anderson cascade impactor, the stages that correspond to each of those particle sizes, and then used an impinger. Also, again, we had the OPCs in line to measure those particle sizes of the particles going through those chambers. Again, on the design, there's 300 mils of volume across those 3 nebulizers, 3 ml per minute, 30 minutes, and the flow rates you can see. We're able to maintain that airflow because that was done between turns of pigs. And so we could set the fans at a certain flow rate, and we did 2 replicates. This is a schematic of how that looked. Here's the circular duct that was installed. Here's your upstream impinger and impactor, and then here's again the OPC. Here's the ESP itself, where the particles are charged. Here's the downstream OPC and the Anderson impactor and the impinger. And so they're able to collect. We have particle size. We have the particle size distributions, etc. This is how it looked on the farm. Here's the nebulizers. Here's the ductwork that was built up into that ESP unit, and all the stuff it took to get that done. It was the team there did an amazing job getting that put together in the field. Before I go on to the results, I think it's important. In the world of filtering pig barns, we talk in MERV ratings, MERV 14, 15, 16. Focus down here. And MERV 14 filter on the E1 particles are classified as 0.3 to 1 micron, about a 75% fractional efficiency. The MERV 15, about 85, 90%. MERV 16, 95% is the definition there. And so that's the world we live in. In bioaerosol engineering, they use 1 minus fractional efficiency, which is penetration, because there is no such, there's filters regardless of type. We work in log reductions. We work in going from some level upstream to some level downstream. So it's important to understand that. So I put this together, a MERV 14 filter, E1, that's a small particle, fractional efficiency of 0.75, so the penetration is 0.25. The log reduction is the negative log of that. You convert it. You're dealing with a 0.6 log reduction. Okay, remember that number? MERV 16, so the same math, we're looking at about a 1.3 log reduction. And so a 3 log reduction, I'm working backwards now, is 99.9 fractional efficiency, or penetration to 0.001. Important numbers to remember as we're trying to compare filters to our outcome on this study. I threw this together. It's just a nice little handy curve. You can look at that and say, well, what's my log reduction? How would that correspond to a fractional efficiency as a MERV rating? Results here. This is just the RNA copies detected up and downstream by stage on the impactor. And so I did is showed up here the log reductions at basically 2.2 to 2.7 log reductions of copies of RNA. using that measurement. Probably more important to look at, or more enlightening, is the log reduction TCID 50 upstream and downstream. On the impactor, these stages run from bigger particles to smaller. There's a lot more big particles there than smaller. And a 2.3 to 2.7 log reduction on those bigger particles. As you get down here, these are pushing down into that 0.3 micron range, the very smaller particles, which we'd be talking about a 0.6 on a MERV 14, a 0.5 somewhere in there, 0.6 on the Impinger. Important to note, these here, they're set at 1.5 log because they could not detect anything. So you set it at that 1.5 log. That's limit of detection of 1.5. So it is possible the log reduction was greater than that shown on all these values here. So that's important to understand what we're dealing with. So to summarize that, highly effective in capturing particles with potentially virus-laden particles entering that chamber, so they cannot enter into the airspace of the pigs. The economics of it, I put this together and with a number of caveats here. We've got the prototype was built for us, and using their numbers, and they don't build commercial scale like we'd be looking at in a pig barn, but based on the cost to build this one, and you take it times some factor to do a hypothetical 2,500 sow farm. The purchase install of the ESP would be about 2.8 million. Number I was given from 2 different contractors to filter a 2,500 sow farm today is about $1,000 a sow. Filter replacement you have in the filter system, and you don't in the ESP. Some maintenance, I put a number in. The pre-filter replacement on the filters. There's an additional electrical cost to run the ESPs. And I'm using some assumptions based on what they gave me for milliamps. We know the voltage at 11 kilovolts. The reduction in fan power because of the reduction in static pressure, or pressure drop. So I plugged this in using data from Best Labs from the University of Illinois. And so I'm back to a net present value, right? So over 15 years, what's my net present value of the systems, putting them fairly close to each other, looking at an ESP. And again, this is using some non-commercial type units scaled up to come with a cost. So I was being conservative in this estimation. So to summarize, ESP is shown highly effective in removing those particles. If you're looking at a standard of a 0.6 or a 0.7 log reduction, we're looking at somewhere in the neighborhood of that being a minimum up to approaching or approaching HEPA, like 99% particle removal, especially on the smaller particles. It's kind of easy to get 95, 98% on the larger ones. And so highly effective in removing those particles, including virus-laden particles. Under the assumptions I just ran with a net present value and plugging some numbers in, it would say about a 25-cent per pig cost increase over filtration. Again, in trade-off for much higher fractional efficiency or collection efficiency. Issues I see are scalability, operational management, operating this in the field with the environmental extremes to which it would be exposed, right? You got snow, you've got rain, you've got cleaning the collector plates at some frequency. Although in the commercial grade, there's automated system to do that. Also the technology, I mean, this requires further design work and investment to look at this, but it looks based on collection efficiency and those assumptions to at least be an option to be explored and with some further study. And so I want to thank the entire group, and I wanted to make sure to leave time for questions, but the entire group at the College of Engineering, Chris and Bernard and Hassan and so on, and the group and the contract growers for their cooperation. Again, SHIC, National Pork Board, and USDA FAR for their funding for this project. Thank you very much.
Thank you so much, Mark, and really exciting to have another potential option for reducing risk via aerosol. We have a couple of minutes for questions. If you raise your hand, we can bring a microphone. Yes.
Really interesting project. Thank you. You mentioned the different MERV ratings for those filters, so the 15s and 16s, and that you had used 14s for your project. Did y'all look at any 15s and 16s at all throughout the course of that project?
Thank you. We discussed it. It was a matter of obtaining them, getting them put in, and having. They're still collecting data, or still were, off the 14. And so we can extrapolate quite readily, knowing those values from 15 to 16. We know the log reduction given the MERV rating, so we can do that very readily with that math. And so, but it would be, again, we would have pressure drops though, which is different, right? So as you increase that MERV rating, you're going to increase your pressure drop. If you didn't, we'd all go HEPA. That's kind of simple math. But depending, the equipment's there, and so if we could add to this study, the hard part's done, getting that installed and fabricated. So potentially we can collect more of that data in the future. I know that negative logs to log conversions are really exciting when it's almost time for beer and dinner. So.
Any other questions for Mark? Okay, let's give him another round of applause. Thank you, Mark.